Hi.
How much you scored, Naveen?
Actually, I scored 80.
80.
Yeah.
Oh my God.
What about stat 2?
That's two. I got around 41. Naveen, which all subjects you have this sem? Maths 2
uh,
and
English too. I
yeah,
got 98 in English too.
yeah, English. Like everyone gets that. Even yeah, English it is fine, but maths, my God.
In quiz one, I scored 88.
Yeah, but English it's fine, but maths you are scoring 80 out of 100. Like you are on next
That's
level.
because he is able to give more time, right? You have stats 2 and maths 2, so it's difficult, right?
Yes.
Okay, then let's begin. So week 10's deadline is tomorrow, right?
Yes, ma'am.
Okay, anyway, today's session we will discuss week 11. We have only two sessions for week 11. Mostly by this weekend, means during this weekend, we'll keep that weekly mock for weeks 9 and 10 so that you can revise weeks 9 and 10 and attempt that mock. And then next week, sometime we'll have mock for end term. So before I begin, maybe Naveen, you can give a what tips to people who like how did you score? Like what did you do right to score well? Maybe you can tell that.
I first of all I prefer to make handwritten notes of what is taught in live sessions. And first of all, I watch all the week's content, and along with the watching the video lectures, I make the notes, handwritten notes, whatever point is important in red pen, black pen, blue pen, whatever. Then I hardly miss any session for maths too. And before going to exam, I revise all the graded assignments and practice assignments along with the notes.
Yeah, this is exactly what is expected actually. So you have to be thorough with the content. Every concept should be clear, then you will be able to get full marks in the exam. And if you look at the questions, there'll be so many questions where you needn't even do any calculation. For example, in quiz, there was the last question in comprehension uh, was that you find the orthonormal basis of the row space and then find out norm of 30 V1 and all that, right? There was one question like this, right? That was for quiz 2. Yeah.
Yes, ma'am.
So in that question, even if you don't know V1, V1 is part of an orthonormal basis. So norm V1 has to be equal to 1. You needn't even calculate V1 for that. V1 is part of an orthonormal basis. So the norm of V1 is always going to be 1. And 30 V1 means it's going to be 30 times norm of V1. So the answer was direct, and we found answers which were like, we were confused, like, how did you even arrive at such answers? So there are certain questions for which you needn't even do any calculation. It will be conceptually, you just think of the concept and then apply the concept, you will be able to get the answer.
I joined little late. Even the final quiz will also be in the same pattern.
We will give you a mock, sir. So for the end end term, we will prepare a mock. So you agree that mock quiz 2 was same as mock quiz 2, right? Like it was not much of a difference.
My
Yeah. So
personal thing, I made the first one wrong, so all the trailing questions went wrong.
for the comprehension, is it?
Not the one that there was five questions related to one.
Yeah.
Everything. That's the first
So
one.
when it's a comprehension question, you know it beforehand that it is a comprehension question, right? It will be mentioned. So you should be very careful because every answer depends on the previous question's answer.
But,
So in that case, you have to be double careful.
no, but you are telling that it is answer. Okay, in the question it is mentioned that answer from this question to this question, like that. Because I didn't notice that.
Okay, I haven't seen it on the portal, but or I don't know, from the way we can see how it will be configured. In that, I see comprehension question.
Or
So
at least the first question, if you give us some alert that this question will be like from this question.
No, one question you can expect like that because means one question will be of that type, and you will be able to identify which question it is because that will be a question where you will be using data of the previous question's answer or something like that.
And one question was very lengthy, but the answer is very straightforward. I don't know why they give one paragraph full of.
Yeah, I think that's the comprehension question. So you will have some introduction for it, how you get the start the thing, and then.
But there was not, that question was very straightforward. Means there was nothing to read and means.
Did you check the solution? Oh, okay, we don't give solution. Okay. Maybe I'll share screen. Just give me 1 minute. I'll just open the quiz paper. So is my screen visible?
Yes, ma'am.
Yes.
Yeah. So the first one, this one we had discussed in live session, right? About this A transpose A and A transpose, how are they related to columns and rows and all that. So
Yeah.
This was pretty easy. And then this question, you just have to get the matrix and all these entries you'll get. So this is, the concept is matrix of a linear transformation. That's it. And this one is straight out of the activity, right? Similar matrices. Then
in those similar matrices,
1 minus 2 to the power 9.
Can you show that?
And this distribution seems to.
What I checked is the sets which you asked that whether they are similar or not. For each of the matrices, I check the determinant, I check the rank, and one thing more which I checked was
trace.
Yeah, the trace. All these were coming out to be same, so I marked that these are similar.
No, that's not the case. No, if they are similar, all these will be the same. But all these being similar does not imply they are means all these being the same does not imply the matrices are similar. So here C is the identity matrix. So the only matrix which is similar to the identity matrix is the matrix itself. So A and B cannot be similar to C. And you can actually find a matrix P such that A and B are similar. So to check whether two matrices are similar, the only thing you have to do is go by the definition. Find a P such that PA is equal to BP. There is no other way.
Okay.
If one of those are not equal, then you can tell they are not similar, but not the other way around. If they are equal, it will not be. It need not be similar.
Okay, got it, ma'am. I marked this question wrong. So
this is straight out of activity. This is one of the activity questions.
So by the rule is that you should go by the definition.
Yeah, for similar matrices, by definition. For equivalent matrices, we have that if the ranks are same, then they are equivalent. That's an if and only if condition. So that is sorted. But
Yes,
for
ma'am.
similar, we have to go only by the definition.
So, got it.
Someone else was asking something, right? Okay. This one is a simple inner product. You just have to check which are the conditions that are satisfied and all that.
This question is
Then,
also similar to, ma'am, one of the, I think, graded assignments.
yeah, and we had done a lot of similar things in activity, and even in the live session, I had given a lot of light on this. And then norm, checking whether it is a norm or not. So all these just conditions. In fact, we have already given you the definition so that you needn't remember what it is. So you just have to look at the questions and then identify which is satisfied, which is not satisfied. And this is a simple affine space thing. So in this, you just have to check for the underlying vector space. So you have to check what is means equal to 0. Whatever is this equation, equal to 0 will be that subspace. And equal to any other constant is an affine space. So you just have to check for that condition. You have given 2 entries here, 2 elements for the basis. So using that, get the equation of the plane. That's it. So, sir, is this what you were telling?
Yeah, this question looks very lengthy, but it's very simple. But I don't know why.
Yeah. So we don't give you the data directly, right? Like here you have to construct, means you have to find out what the linear transformation.
Took time actually.
So this is the comprehension question. Means it's comprehension because it is comprehension, no? Means you have to read it and then you have to answer accordingly. That's why it is a comprehension question. And all the comprehension questions means all the questions that follow the comprehension will be interrelated. So from this you will get the linear transformation and then find the matrix of the linear transformation. Carefully do the, because once you get the answer to the 7th to this question, only then you will get the answer correct for the 8th question. So everything depends on the previous answer. And then, okay, yeah, the kernel you can directly find from the linear transformation itself. And then here you have a Gram-Schmidt process applying. So here, yeah, this is what I was telling. 30 times V1. V1 is already a part of an orthonormal basis. So norm V1 is equal to 1. So norm 30 times V1 is just 30 times norm V1. So the answer is 30. So yeah, like for 10A, you didn't had to anything. Like you just have to read the question without any previous data. You could have written the answer as 30 because V1, V2 is an orthonormal basis. If B, C, D and all, you have to calculate, but 10A was straightforward. Okay. So we will discuss week 11 today. So in week 11, we will be discussing higher order partial derivatives. Means, so you already know how to calculate the partial derivative of a function, multivariable function. We are dealing with multivariable functions. That is why we have partial derivatives, right? If I had a function of one variable, it would just be f dash of x, right? The usual derivative. Since I have a function of more than one variable, so when I want to talk about the derivative, there comes a confusion of with respect to what? There are multiple variables. So derivative with respect to what? So with respect to x, if I say, then that's the partial derivative with respect to x. And how do we get the partial derivative with respect to x? How do we evaluate fx?
Consider only the components that involve x and keep the others
treat
as
y
constant.
as a constant. Yeah.
Yeah,
Right.
keep others as constant and consider only the components involving x and differentiate.
Yeah. So we will treat y as a constant and then you do the usual differentiation to get fx. For fy, you treat x as a constant and then do the usual differentiation to get fy. Okay. And we also know, using the limit definition, what is fx and fy. So fx is limit h tends to 0, f of x plus h comma y minus f of x comma y by h. So here there is a change only in the variable involving, means the terms involving x. So there is a change along the direction of x. So there alone we will have a change. For fy, there will be a change only for the y component. So these are the partial derivatives, the first order partial derivatives. So if I have a function of two variables, I have two first order partial derivatives. Now we can, when we have a function of one variable, we have f dash, we can talk about f double dash, f triple dash and all that. So these are the higher order higher order derivatives. Similarly, we can talk about higher order partial derivatives. So when I have a function of one variable, what is f double dash basically?
Differentiating it twice.
You differentiate the derivative, right? You have a function, you differentiate it once to get the derivative. You differentiate the derivative to get the second derivative. So you're differentiating the derivative itself to get the higher order derivative. So similarly, here we have higher order partial derivatives. So you differentiate the partial derivative itself partially to get the next second order partial derivatives. So I have two first order partial derivatives, fx and fy. So fx is going to be a function of x and y. Fy is going to be a function of x and y. So I can differentiate fx with respect to x, fx with respect to y, fy with respect to x, and fy with respect to y, right? So I can have four partial derivatives, right? When I have a function of two variables, second order. Agreed?
Yes, ma'am.
Yes, ma'am.
Okay. So how is it going to be by definition? What is fxx? So how do we represent it? It is dou f by dou x. You're differentiating this with respect to x, dou by dou x. So this is represented as dou squared f by dou x squared. This is similar to what we had in usual derivative. Here we'll write d squared f by dx squared. Instead of d means the total derivative, dou means the partial derivative. So dou squared f by dou x squared. This is going to be the same limit. You're going to do partial derivative with respect to x of this function. So limit as h goes to 0. Instead of f, you'll have fx. The partial derivative with respect to x and the changes in the x component alone. So is it clear how we get the second order partial derivative of f with respect to x?
Yes, ma'am.
Yeah. So similarly, we can do fy y. So fy y, okay, this is fxx. We represent it as fxx, fy y. So this is dou by dou y of the partial derivative with respect to y. So dou squared f by dou y squared. This is again the same limit. The function fy is differentiated with respect to y. So there will be a change in the y component alone. So then we have the mixed partial derivatives, that is fx with respect to y and fy with respect to x. So with respect to different variables, we are differentiating. So that is called the mixed partial derivative. When I differentiate fx with respect to y, I denote it as fxy. So what am I doing here? So how will I write it in this notation?
Dou divided by dou y
Yeah.
dy
into
Dou
dou
f by dou x.
divided by dou x.
Yeah. So when we write it this way, it's going to be dou squared f by dou y dou x. So you see that this is interchanged when we write it in this notation. So you have to be careful with that. fxy is fx with respect to y. So when we write it in this notation, it's going to be dou squared f by dou y dou x. But there's nothing to be confused about, because once you reach this stage, you know what you're actually doing. So with respect to y, you're differentiating, and the function is fx. So fx with respect to y, so there'll be a change in the y component alone. And then we have one more partial derivative, that is fy with respect to x. So that's fyx, and this is dou by dou x of dou f by dou y. So that's dou squared f by dou x dou y. Again, here in this notation, it's dou x dou y. And when we write it this way, it's fyx. But again, you reach this stage and you're clear what is happening. So this is limit as h goes to 0, fy with respect to x. So x plus h comma y minus fy x comma y by h. So when I have a function of two variables, I have four partial derivatives. So what if I had three variables? F of x comma y comma z. What are the first order partial derivatives?
Fx plus y
fz.
And then second order would be
F xx xy xz.
FZ.
Yeah, each this function with respect to each of the three variables. And then here total 8, yeah, fyy fyz. And then for this again 3, fzx fzy fzz. So when I have three variables, I have 8 second order partial derivatives. So like that you can find out partial derivatives for a function of any number of variables. So here I have n variables, f of x1, x2, xn. So how many second order partial derivatives will I have?
N squared.
n square.
N squared.
No, n squared means, okay, yeah, fine, sorry. So here it's 9, right? Not 8.
Yes.
So here it's 9. So we'll have n squared. Okay. So yes, this is how you define partial derivatives, the second order partial derivatives.
Ma'am, it's 2 power n, right?
That's what I'm thinking. Did we get 9
Yeah,
here
it's 2
or
power
8?
n. It's 2 power n.
1, 2,
It's 8
3,
only.
4, 5, 6, 7, 8, 9. 9, right? So how, what is the permutation happening here? I have 3 variables and I have 3 variables and I want the second order partial derivatives. Okay, so I'll have this and then each with respect to each of this is with respect to 3, means each of the 3 variables. So that would be
3 into 3.
3 into 3, right? Yeah, 1, 2, 3. 3 into 3. So that's going to be n into n, right?
Yes.
Okay.
Now, in this second component, you have written fyx, fyy, and fyz. This means partial second derivative, higher order, your second derivative of y with respect to x, then y with respect to y, and then y with respect to z.
Yeah. Okay. Yeah. So here we have fxy and fyx. In general, they need not be equal. They will be equal only under certain conditions, and that is given by the Clairaut's theorem. So in general, they'll not be equal. But if fxy and fyx are both continuous, then they will be equal. So if we have a function f, okay, here it is of n variables. So you know what an open ball is and all that, right? What is an open ball around the point?
No, ma'am. I didn't understand that. Just drawing a circle, is it?
Yeah, an open ball means that, so when you have a function of one variable, when we have just f of x, so the number that we consider, that f of x, that x is a real number, right?
Okay.
So x is going to be somewhere here. When I talk about an open ball around x, suppose I say open ball of radius 1. So what I want to do is I will go at most one distance on either side. Yeah. So when it is just one variable, it's going to be an interval, right?
Correct.
And every point in this interval is going to satisfy the condition that the distance from, say, if this is x naught, distance of any point from the point x naught is going to be less than 1, at most
Less
1.
than 1. Yes.
Yeah.
Yes.
So
Less
this
than
concept, okay, open ball means you don't consider the endpoints. So less than or equal to you don't consider. Yeah.
Okay.
So this concept, when it happens in R2, what happens? So you have a point here. If I want to move a maximum of one distance, what will I get when I
I
move a
can go
maximum?
either x. I can go x.
It would be a
x axis or-
circle.
I can move this way, this way, this way, this way, any way, right? So the maximum I can move is within this circle. And I can write this circle as, okay, it is the set of all points such that distance of that point from x naught is at most 1, right?
Ma'am, less than radius of that circle, like that.
Yeah, I'm taking a unit ball. Unit ball means, okay, fine, let's keep it R. So it's a open ball of radius R, means you can move a maximum of R distance, R units. So this, you agree with this, right? It is distance of any point in the ball from the point x naught is going to be less than R.
Ma'am, close ball. It is
Close ball means less than or equal to. You're allowed to move up to a distance of R. It can be, the distance can be equal to R. Then it is a closed ball. If it's an open ball, you're not allowed to go R distance, but any distance less than R is okay.
Okay.
Yeah. So what is this in R2? What is this distance? What is the usual norm that we define? Square root of x minus x, that thing, right? What the usual distance, x minus
X
minus
minus.
the whole square plus y2 square.
Yeah, okay, so let's call this x1. Okay, the notation is bad. Okay, you understand. X minus x1 minus x naught 1 squared plus x2 minus, okay, I denote x as x1, x2 and x naught as x naught 1 and x naught 2. x2, x naught 2 squared. So this is nothing but a circle, right? This equation is the equation of a circle. Right? When I square on both sides, I'm not circle, it's a disk. All points within that circle. Right? Yeah.
Yes.
So this concept is generalized in Rn also. Instead of 2 components, you will have n components, that's all. So in Rn also, since we will not be able to draw it, you can visualize it as a, in R3, it's going to be a sphere, right?
Yeah.
So like that in Rn, it's going to be whatever that shape, figure is. So let's imagine a sphere or a circle, a disk. Okay. So yeah, if we want to talk about the mixed partial derivatives being equal at a point, we want the partial derivatives to be continuous in an open ball containing that point. So if I want to talk about the continued partial derivatives being equal at this point, I want both the partial derivatives to be continuous in an open ball around that point. That's all. So if the both the partial derivatives are continuous, then they are going to be equal. So fxy need not always be equal to fyx, but if both of these functions fxy and fyx are equal, continuous, then they will be equal. And all the functions that we will be dealing with are mostly continuous functions, so we can ignore this. Means the order, you can ignore the order, because we'll be mostly dealing with continuous functions. Polynomials are the simplest continuous functions you can think of, right? All polynomials are continuous. Rational functions, when the denominator doesn't vanish. All these are continuous functions, right? No? Aren't they?
Sorry, ma'am, could you repeat the question?
All polynomials are continuous functions, right?
Right.
Yes.
Yeah. So we'll be mostly dealing with polynomials only. Polynomials or rational functions and all that. So mostly means most of our functions will be continuous. So you can always ignore the order in which we differentiate. So yeah, this is not only for second order partial derivatives. This is for any higher order partial derivative also. So yeah, that's what is mentioned here, the kth order partial derivatives. The kth order means you differentiate a function k times, and with respect to whatever variables, whatever order you want. And it's the same notation that we'll be following as we did for the second order partial derivatives. And we have a Clairaut's theorem there as well. So there again, it's the same theorem extended to the whatever kth order partial derivatives. So if you want two kth order partial derivatives to be equal, means the mixed partial derivatives, then you want both of them to be continuous. And if they are continuous, then the order in which you differentiate doesn't matter. That's all. Okay, so is the Clairaut's theorem clear what it says?
Ma'am, can you explain with the example?
Yeah, I'll do that. So yeah, okay, let's do that. Now we have a function here. Is this function continuous?
Yes.
Yes.
Yeah, it's a polynomial function, so it is continuous, no issue at all. So once you calculate fxy, you needn't calculate yx. They will be equal, right? Because this is a polynomial function, this is a continuous function, all its derivatives are going to be continuous, so no problem at all. So in this case, once you calculate fxy, you need not calculate fyx. But anyway, let's do everything. So what is fx here?
2x y cube
2x y cube minus y plus 6.
Yeah. And fy is
3x squared y squared minus x plus 8.
Plus 8. Okay. So now let's calculate the second order partial derivatives. So fx with respect to x.
2y cubed.
Yeah, that's all. Fy with respect to y.
6x squared y.
Okay. Fine. That's fxy. So that's fx with respect to y.
6y.
6xy squared.
6y squared.
6x
What is it?
squared.
Just 6x and
Minus 1, no?
Yes.
yeah.
Okay. So we needn't calculate fyx because we know that these are continuous functions, but still let's calculate fyx. So this is fy with respect to x.
Same ma'am. 6x squared y minus
Yeah. 6x squared y minus
x
1.
y 6xy squared.
Yeah. 6xy squared minus 1. So these two are equal. And because these two means this function is a continuous function, the mixed partial derivatives are both going to be equal.
Ma'am, I have a question. We are saying that if they are continuous, then they will be equal. Can we also say vice versa? That is, if they're equal and they both must be continuous in that open.
So you're talking about the converse of the Clairaut's
Yes.
theorem, right?
Yes.
It doesn't hold straightforwardly. There is something more to it.
Okay.
Yeah. Yeah. So in the lecture, sir has given an example of a function where it is not holding true, right? Xy, some x squared minus y squared or something. I don't remember exactly. Something like this.
This is not a polynomial.
This is not a polynomial, but the partial derivatives will not be continuous at that point, whatever, at 0, 0. Other than 0, 0, everywhere else it's continuous, right?
I have not seen the lecture yet.
So f at 0, 0. Is f continuous at 0? First check that. Because that's the only problematic point, right? Every other point, it's going to be a continuous function. Why?
I think it's not defined because the denominator would become 0 at x and y equal to 0, 0.
No, but then it's defined separately for 0, 0, right? It's defined as 0.
It should be continuous, ma'am. The concept you explained in one of the live sessions, that see the power in denominator and numerator. So when I see the power in numerator, it is, say, 4.
Okay.
It would be approaching 0 faster than the denominator. So it would be 0. The limit would be 0.
The limit would go to 0 fast. Okay, fine. This is fine. My question is it continuous at any other point, x comma y, not equal to 0, 0? Is it continuous at all other points is my question. Why? Why is it continuous?
Region of two polynomials.
You can see it as a composition of functions, right?
Right.
So these are my functions. X squared plus y squared. All these are continuous functions. And I know product of continuous functions is continuous. Quotient of continuous functions is continuous. As long as the denominator doesn't vanish. But because x comma y is not equal to 0, 0, the denominator does not vanish. So this is a continuous function. Because I can write it as bits and pieces of continuous functions and then use product and quotient and all that. You can think of it as a composition of functions. So it is a continuous function. Yeah, you can think of it as a composition of functions as well. But yeah, here we have used product and quotient. Product of two continuous functions is continuous. Quotient of two continuous functions is continuous. Using all that, we can tell that this function is continuous at all points other than 0. At 0, 0 also, you can check whether it is continuous or not using the definition, the limit. Check the limit. If the limit is equal to f of 0, 0, that is 0, then the function is continuous. But that's not what we have to actually check. We have to check for the continuity of fxy and fyx. So after this, you calculate what is fx, what is fy, what is fxy, what is fyx. And then you check that these two functions, or at least one of them, is not continuous at 0, 0. And because of that, these two will not be equal. Sir has done all the calculation, so you can check that. So continuity of the partial derivatives, the mixed partial derivatives, is a necessary condition for the mixed partial derivatives to be equal at a point. Fine. So let's not break our head too much on that. We'll deal with a simple continuous one.
It is not equal to, then it is not a continuous mixed partial derivative.
So the mixed partial derivatives, they are not equal, which means that at least one of them has to be discontinuous, right? Because the Clairaut's theorem says if both are continuous, then they'll be equal. If they are not equal, then one of them is not continuous. That is why there is a problem, right?
Yeah.
Okay, so let's get to simpler ones. So here we have a function of 3 variables. Find the second order partial derivatives. So first find the first order partial derivatives. What is fx?
Minus 4x cube plus 4x y square z square
Minus z bar. Maybe we'll do only one set. You can do the others because it's a continuous function. You just have to differentiate it by keeping the other variables as a constant and all that. So what is fxx?
Minus 12x square plus 4y squared z square.
Yeah. What is fxy?
8xy z square.
And fxz?
8xy squared z minus 4z cube.
Yeah. So once we have found out fxy and fxz, we have found out other two also, right? This is a continuous function, means it's a polynomial. So all the derivatives are going to be polynomials and they will all be continuous. So in this case, it's simple. Okay, so similarly, you find out the others, fy, fz, and then the corresponding other partial derivatives. Okay. Okay, yeah. Next, what is the Hessian matrix? So once you have the partial derivatives, we can talk about a matrix whose entries are the partial derivatives, and that is called the Hessian matrix. So if I have a 2 cross 2 means a function of 2 variables, then what are the possible second order partial derivatives?
fxx,
fxx, fxy, fyx, fyy.
Yeah. So these are the second order possible second order partial derivatives. So using this, I can write down a matrix. So the matrix is nothing but this fxx and then fxy, or will it? I think it will be f by x, fxy and fyy. So what you do is every column will be gradient differentiated with respect to one of the variables. Yeah, so let's check if it's written correctly. Rho squared x1, so there's going to be rho squared f by rho x1, rho x2, and this is going to be f x2, x1, right? Yx, correct. Right. So what you do is every column you take the gradient of f. So the gradient of f is fx comma fy, right? This is the gradient of f. Correct? Yeah. So you differentiate the gradient with respect to x, and then you will put that in the first column. Or are we putting it in the first row? What's happening here? Rho squared f by rho x1 squared. What is this? Yx, right? F
Yes.
Yx. Okay, and then here it's going to be f xy. Okay, so the matrix that we have written down is correct. Okay, so every row, you differentiate every row with respect to that variable, and then you get the, means you differentiate the gradient with respect to each variable and get each row. Okay, so you differentiate the gradient with respect to x, you get the first row. Differentiate the gradient with respect to y, you get the second row. And okay,
When we differentiate the gradient with respect to x, we get as fxx and fxy, no ma'am?
fxx and fyx, no, fy with respect to x.
Okay, okay, fine.
Ma'am, one doubt. In the last one, so when all three are equal, then only it will be continuous.
No, no. Here we have to consider only a pair, right? I'm considering only second order partial derivatives. So second order partial derivatives means it's either going to be, it's going to involve only two variables, right?
So fxy is equal to fyx. If that is equal, then it is continuous, and fxz is equal to fzx. Then it is continuous.
If these two are continuous, then those two will be equal.
Okay.
When
so
we
don't
talk
have
about
to check for all
triple, when I talk about the, no, what is the third one? This is one, this is the second one. That's it, right? Only two, right?
Okay.
When we talk about f, x, y, z, then we have multiple cases. F, y, x, z, f, z, y, x. So if all these three are continuous, then they will be equal. We have much more also, right? X, Y,
Right,
Z.
yes.
Yeah, so like that.
Okay, thank you.
Okay. So yes, the Hessian matrix is just this. You take the gradient of the function and then differentiate it with respect to each variable and put it as rows. That is the Hessian matrix. So if I have n variables, I'm going to get an n cross n matrix, right? If I have two variables, I'll have four partial derivatives. Oh yeah, this is what we had seen earlier, right? If we have n variables, we have n squared second order partial derivatives. So we'll put all that in a matrix in this order, and that's going to give the Hessian matrix. And using this Hessian matrix, we can do a lot. And once we have a matrix, what are the different things we can think about? First of all, it's a square matrix. So what's the first thing that comes to our mind?
Determinant.
Yeah, we can talk about determinant of the matrix, the trace and all that is possible because we are having a square matrix. And since now we have matrices, we can talk about rank of the matrix, nullity of the matrix and all that. Yeah. So yeah, let's do a problem. So let A denote the Hessian matrix of this function, find out A. So if we have continuous functions, we needn't think about all this, right? We needn't get confused about what is what and all that, because if we have continuous, if we have polynomials, as simple as that, if we have polynomials, all my derivatives are going to be polynomials and they are all going to be continuous. So this problem will be sorted. So in that case, what is the matrix that we get? What will the Hessian matrix be when the mixed partial derivatives are equal?
An identity matrix.
No, why identity? Why should it be 0? It can be any other number, no? It can be 2.
Scalar matrix.
No, not a scalar matrix. Scalar matrix, again, this is off diagonal entries. These are not the diagonal entries.
Symmetric.
Symmetric matrix.
Yeah. This will be a symmetric matrix. A will be equal to A transpose, right? Because these two entries will be the same. So this will be equal to this. This will be equal to this. So this portion will be equal to this portion. So you'll get a symmetric matrix. And when you study about eigenvalues and all that in MLF, why symmetric matrices are nice, you will know that. Okay, so yeah, let's quickly calculate the partial derivatives. We'll write down the Hessian matrix here. What is fx for this?
6x square plus z.
6x plus z, right?
Yes.
Fy is
2z.
2z.
Fz is
X plus 2y minus
X plus 2y minus 2z.
So I have three variables, so I'll get a 3 cross 3 matrix. What is fxx?
6.
6.
Fxy is
0.
and that's also going to be equal to fyx, right?
Yes.
And fxz is
1.
1.
and that's going to be equal to fzx. Fyy is
0.
0.
okay 0 and fyz
2.
and that's going to be equal to fzy and fzz is
0.
minus 2, no?
Sorry, ma'am.
Yeah. So when we write it down as a matrix, fxx, fyx, right? Yeah. fyx, fzx, fxy, fxz, fyy, fzy, fyz, fzz. This is the Hessian matrix, and that's going to be equal to 6, 0, 0, 1, 1, 0, 2, 2, minus 2. So this is a symmetric matrix. This function is nice that all your second order partial derivatives are constants, but you might even have terms containing x and y. The highest degree here, the highest power is 2. So the second order partial derivatives are all going to be constants, right? If it had a cubic term, then we would have had functions of x, y and all that, right?
Ma'am, again can explain what you said. I missed.
So what I'm telling is this matrix need not always be a matrix of numbers. You can have something like this, 6x, y squared, something like this you can have. But here in this case, these are all numbers because this function, the highest power that this function has is 2. So when we take second derivative, I'm going to get numbers, right?
Yes.
Yeah, if I had a cubic term, then I would have had some function of x, y, or z, right? When I do differentiation twice. So, yeah. So now we can talk a lot about this matrix. We can talk about the determinant, what else, rank and all that. So what is the rank of this matrix quickly?
Two, ma'am.
I think it will be 3. Let's check. 6, 0, 1, 0, 0. Okay, you can check the determinant, right? What is the determinant? We'll expand along the second row. So that's going to be minus 2 times 6 into 2 minus 0. So it's non-zero,
Rank is
right?
3, ma'am. Rank is 3.
The determinant is non-zero, so rank is 3. You just had to check the determinant, 3 cross 3, right? And if the determinant was 0, then you have to then proceed to do the row echelon form and all that. But anyway, can you see that the first column and the second column are linearly independent? This is linearly independent, right?
Yes.
Yes.
Yeah. So the rank is at least 2, right?
Yes.
Yeah. So if you calculate the determinant, if it is 0, then you can tell the rank is exactly 2. If the determinant is non-zero, then the rank is 3. Here, because the determinant is non-zero, the rank is 3.
But third column is also linearly independent, right?
Yeah, yeah. Because third column is also linearly independent, that's why determinant is non-zero. No, I'm telling in the very first look, checking 2 vectors are linearly independent or not is easier than checking 3 vectors, right?
Yes.
Because for 2 vectors, I just need to check whether one is a scalar multiple of the other. So that's why I wrote this down.
No, but how will we find the determinant of 3 by 2 matrix?
No, I'm always going to get a square matrix. No, I'm always going to get
at
an
the
n cross
bottom
n.
you wrote now that first 2 vectors only.
So no, this says rank is greater than or equal to 2, right? When
Right.
this happens.
So we will find the
check.
determinant of the matrix only.
Oh, yeah. Of the matrix, yes.
Okay.
Yeah. Okay. Here we have a cubic term. So my Hessian matrix is going to contain functions of x, y, or z, right?
Yes.
Yeah. So let's quickly do what is fx?
2xy.
Okay, 2xy. Fy is
x squared minus 3y squared.
Fz is
2y cubed.
Right?
Fy
Where
would be
z is square. Fy is equal to
x squared minus 3y squared z squared.
Okay. What is fxy? 2x. Oh, I didn't calculate fxx. Fxx is 2y. Let me write that order. Y. And fxz is 0. So from here we have fyx, and from here we have fzx. Okay, what is fyy?
Minus 6y.
6yz squared.
Fyz is
minus 12yz.
No, y12 minus
6
y squared z. And this is going to be equal to zy as well. What is fzz? Minus 2y cubed. So the matrix is 2y.
FZ is 0, na? FZZ is 0.
No, here there is a z, no? So this with respect to z.
Second time there will not be any z number. No? Okay, right, understood.
2x, and then this is 0, 0. This is minus 6y squared. This is minus 6y squared z. Oh, yz. Minus 6y squared z, and then here we have minus 2y cubed. So this is the Hessian matrix. And what is asked? At the point 1, 1, 1. So Hessian matrix at the point 1, 1, 1 would be put x is equal to 1, y is equal to 1, z is equal to 1.
So
that's
what will be the value of fyz, ma'am? Can you do the calculation once more? Fyz should be 12y minus 12y square z.
Fy is
fyz.
Fy is correct, is it?
Fyy is correct. Okay. Fyz.
With respect to z, this is 0. So here when I differentiate with respect to z, it's going to be minus 3y squared into 2z.
Yes.
So minus 6y squared z.
Okay, 6y squared z. Okay.
So this is going to be 2, 0, minus 6, minus 6, minus 6, minus 2. So this is the matrix. Now the question is, okay, this is A. A is H of 1, 1, 1. What is the rank of A? What is the nullity of A? Okay. 1 1 1 1 1 0 0 2 minus.
Can't we use the same method like finding the determinant and
Yeah, we can use that, but what if the rank is 1 or 2? We'll not know, no? So we can do that. Okay, let's check. 2 12 minus 36 minus 2 minus 4. Okay, it's non-zero, right? Okay, determinant is non-zero. So rank is 3, nullity is 0. I was thinking the determinant may be 0. That's why I was doing row echelon form. Fine.
okay.
Okay, so is it clear what we did? We are just doing a step-by-step process.
Yes, sir.
Yes, sir.
Okay. Okay, so yeah. Do you remember the second order, second derivative test for functions of one variable to check maxima and minima? If we have a function of one variable, how do we check whether a point A is a point of maxima or minima? Do you remember that?
F dash of x is 0.
So we'll first find the critical points.
And f double dash and then f double dash of x should be lesser than 0 for maxima and greater than 0 for minimum.
Perfect. So x is equal to A is a point of maxima if f dash of A is 0 and f double dash of A is less than 0. The second order derivative is less than 0. And it's a minima if the second derivative is greater than 0. So first step is to find critical points. Now here, what is the critical points we will have? Means how are we going to get the critical points? Because we don't have the usual derivative. Instead, what do we have?
Gradient.
Yeah, we have the gradient function, which acts like derivative for us in the multivariable case. So first we will find out the critical points, and the critical points are those points where the gradient of f is equal to 0. So fx should also be equal to 0. Fy should also be equal to 0 if it is a function of two variables. If it's three variables, then fz should also be equal to 0. Okay, so now let's consider it for two variables. So we want both the partial derivatives to be 0. So yeah, critical points were those points where the derivative was equal to 0 or the derivative does not exist. So similarly here, the gradient is equal to 0 or the gradient does not exist. Yeah, so those are the critical points of the function. So here if we have a function and its first and second order partial derivatives are continuous and local. Okay, so we are assuming that the partial derivatives exist. So the critical points are got by putting the derivatives equal to 0, the gradient function equal to 0. Okay, now we imitate the same, what we did for the one variable case, for the multivariable case as well. In the one variable case, the Hessian matrix is a 1 cross 1 matrix, right? Because we had only one variable, we will have only one second order partial derivative. There we had a 1 cross 1 matrix. Here we will have a 2 cross 2 matrix because we have two variables and then we'll have 4 second order partial derivatives. So here what the condition says is this: fyx, fxy, fyy. So here we want this entry to be greater than 0 and the determinant of the matrix to be greater than 0. Okay, the first thing we will check is we will first find the determinant. If the determinant may be greater than 0, less than 0 or equal to 0, right? The determinant is going to be a number because we will evaluate it at the point a comma b. So if the determinant is equal to 0, the test is inconclusive. If the determinant is less than 0, it is a saddle point. If the determinant is greater than 0, then you check for fxx. If fxx is also greater than 0, then it is a point of minima. If fxx is less than 0, it is a point of maxima. So what you have to remember is this. You have this matrix. You first check for the determinant and then you check for the first diagonal entry. First of all, the determinant has to be greater than 0. If it is equal to 0, you cannot tell anything. The test is inconclusive. If it is less than 0, it is a saddle point. So only if it is greater than 0, you go for further investigation. The further investigation step is check this diagonal entry. If the diagonal entry is positive, it is minimum. And if it is less than 0, it is maximum. Is it clear?
Yes.
What if the second order is equal to 0? Exactly.
This term, is it?
No. Can you scroll up a bit? So here you have two conditions, right? Second derivative of a is either smaller than 0 or greater than 0. What if it is exactly equal to 0?
In this case, the test is inconclusive.
Okay.
That's what happens here. The determinant becomes 0. If this term is 0, then the determinant of this 1 cross 1 matrix is 0, right?
Okay.
Okay, so this is the test for checking whether a point is a local maxima or minima when we have functions of two variables. In fact, we have the conditions for three variables as well, right? It's simpler if you know the concept of a positive definite matrix or eigenvalues. So that maybe when you do it in MLF and then you will realize that, okay, yeah, this is how it was related. Since we are not dealing with eigenvalues, for us, we will keep these conditions in mind. In fact, if we know the eigenvalue concept, we can define for any function of n variables. But anyway, here it is. This much is enough.
So how will we do it if for 3x3 matrix comes in the exam?
We will check. We'll first finish this, and 3x3 I have included. So when 3x3 comes, I'll tell you there.
Okay.
Yeah, I think I've included. Yeah. Okay, so let's do this. Discuss the local extrema of this function. What is the first thing we will do if we want to find out the local extrema?
Let's see, find the
second.
First, find the critical points, right? The first step is find out the critical points. What is fx?
3x square plus
2 plus 2x.
Yeah. I want fx to be equal to 0 and fy to be equal to 0. What is fy?
2xy minus 1. Oh, x squared.
X squared minus 1, right? Yeah. So from here, we will easily get x is equal to plus or minus 1, right?
Yes.
Yeah. So what do we get from here? X into 3x plus 2y equal to 0. So x is equal to 0 or 3x is equal to minus 2y. X is equal to 0 is not possible, right?
Yes.
Yeah. Because if x is equal to 0, then fy is not equal to 0. So this is ruled out. This only has to happen. So from here, what do we get? Y is equal to, when x is plus 1, it is minus 3 by 2. So this happens when x is equal to 1. Or when x is equal to minus 1, what do we get? 3 by 2. Yeah. So it's 1 comma minus 3 by 2 minus 1 comma 3 by 2 are the critical points. Agreed?
Yes.
Okay. So what is the Hessian matrix? Let me write down the matrix directly. What is fxx?
6x plus 2y.
Yeah. And fxy is 2x. Fyy is
0.
Okay. So now at each of the critical points, I have to check those conditions, all these conditions. So what is the Hessian matrix at 1, 3 by 2, minus 3 by 2? 6 minus 3. 3. 2, 2, 0. What is the determinant of this matrix?
Minus 4.
Minus 4.
Minus 4.
So it is a
saddle point.
Yeah. If the determinant is greater than 0, only then further investigations. If the determinant is less than 0, we stop there. This is only for the 2 cross 2 case, okay? And what about h of minus 1, 3 by 2?
Minus 3.
Minus 3, minus 2, minus 2, 0. Here again, it's saddle point, I guess, right? 0, minus 4. So this is also a saddle point. Both are saddle points. Okay.
Ma'am, so we can say this does not have a local
Maxima or
minimum.
minimum.
Yeah, and so it doesn't have a global minimum or maximum also. Global minimum and global maximum.
Actually, the concept of global minimum maximum, so infinity is global maximum, right? Means you can take this function to infinity, right?
Okay.
And you can also take this function to minus infinity. So if you look at the global maxima minima, it's going to be infinity and minus infinity.
Yes.
Yeah. So the concept of global maxima and minima makes sense when we have a bounded domain. Means if you're talking about the function within certain conditions, then the concept of global maximum. Otherwise, you can always, polynomial functions, you can always take them to infinity or minus infinity. So just because it doesn't have local maxima minima doesn't mean it doesn't have global maxima or minima.
So then only it will become saddle point, no? Because there should be some maximum minimum after saddle point.
So after that, what happens?
To become a saddle point, there should be a minimum post that, and before that there should be a maximum. Means from saddle point there should be one maxima on right side.
No. Saddle point means that there are points. This is the point. This is a critical point first of all, because the gradient is 0 there, and near that point you have values of the function which are bigger than the values attained here and smaller. That doesn't guarantee that there is a minima or maxima nearby. It just says that there is some kind of a fluctuation happening nearby, and hence it is neither maxima nor minima.
Slope changes.
It doesn't guarantee anything more than that.
Because there are two types of curvature. One side it is less and other side it is more.
Yeah.
Slope changes its direction.
Yeah. X cube plus x squared y minus y. Let's see how it looks here. So z is equal to cube
plus
x squared y
minus y.
And what is the point? 1,
minus 1, minus 3, minus 1.5.
So, yeah, at this point. The value of the function, okay, let me put the value also. Or is it hard to calculate? 1 plus minus 1.5 minus 0.5 plus 2x, right? Ah. No, it's not. 1 minus 1.5 is minus 0.5, 1. Yeah. So this is the point. This is the critical point where there is a change. But if I take a ball around this, there are points where the value of the function is bigger and smaller. So smaller is straightforward visible. Bigger is this side. Is it clear what I'm trying to tell?
Yes.
Yes, ma'am.
So we have a saddle there. And those are this point and this point. Those are the only 2 points where the gradient vanishes. So those are the critical points and those are the possible candidates for maxima and minima. Okay. And then let's quickly do this problem. What is fx?
2x minus 2xy.
Fy is
3y minus 3y square minus x square plus 1.
Okay. So I want both to be equal to 0. Solving this one is easier. 2x, 1 minus y is 0. So x is equal to 0 or y is equal to 1. Okay, so when x is equal to 0, what happens to fy? So y is equal to
1 by 3.
Root 3, right?
Root 1 by root 3.
Yeah. And when y is equal to 1, fy is when y is 1 minus 3 plus 2 minus x squared minus 2 is equal to 0. So x is equal to plus or minus 2i, right? Okay. This is not going to happen, right? Did I do the calculations right? Y is equal to 1 minus 2.
Yes, ma'am, you did.
Right. So this is not possible. So this is the only possibility. So we have 2 critical points, 0, 1 by root 3, 0, minus 1 by root. What is the Hessian matrix here? Fxx. 2 minus 2y.
2y.
Fxy, x with respect to y.
Minus
2x.
Minus 2x. And then fyy. Minus 6y.
6y.
Yeah. So what happens at 0, 1 by root?
2
minus 2 by root 3. 0.
Minus
0. And minus 6 by root 3.
Okay. What is the determinant here? Some positive number, right?
Some positive.
Yeah. 2 or negative. No, 2 minus 2 by root 3 is positive. Okay,
Positive.
so it's a negative number, right? Yeah. So saddle point. What about the other point? Other point also is, oh no, it may make a difference.
Plus
1 by. So it's going to be 2 plus 2 by root 3, 0, 0, 6 by root 3. Here the determinant is greater than 0. Yeah. So determinant is greater than 0 and this entry is greater than 0. So it's a point of
Minimum.
Yeah. It's a local minimum.
In what case fx this fxy is equals to fyx? You have explained, I think.
If fxy and fyx are both continuous, they will be equal. Here we are dealing with polynomials, no? So all derivatives are going to be continuous. And that's why we directly wrote fxy is equal to fyx.
Ma'am, in the above question, there is no extreme. There is only two saddle points.
We have only saddle points. We have only two critical points and both are saddle points. There's no local extrema. Yeah. So there is no local extrema here. We have only two saddle points. Here we have a saddle point and we have a local minima. Okay. Let's do this one. What is fx?
6x square plus 6y square minus 150.
We want this to be equal to 0 and fy is 12x minus 9x. So this is easier to calculate. So 3y 4x minus 3y equal to 0. So y is equal to 0 or 4x is equal to 3y. Okay. So when y is equal to 0, what happens to fx? 6x squared is equal to 150. X squared is equal to 50 by 2, 25. X is equal to plus or minus 5. 5 comma 0 and minus 5 comma 0. What happens when 4x is equal to 3y? 6x squared plus 6 times y is 4 by 3x. 4 by 3 x squared minus 150. I'll put equal to 150. So this is 2 6x squared plus
32 by 3x squared.
32 by 3x squared is equal to 150. So let's cancel a 2 everywhere. 16, 3, 75. 9x squared plus 16x squared is equal to 3 into 75. 9 plus 16 is 25. Squared is equal to 3 into 75. So this is 3, this is 9. So x is equal to plus or minus 3. So when x is plus 3, y is 4. When x is minus 3, y is minus 1. So we have 4 critical points. What is the Hessian matrix here? fxx, 12x. fxy is 12y. fyy is minus 18y. Okay. So what happens at 5 comma 0?
I think
Ma'am,
is something else. FYY is
Oh, okay.
12x
12x minus 18y.
18y.
Okay. So this is 60, 0, 0, 60. So this is what? Determinant is positive and the diagonal entry is positive.
minimum.
Yeah. This is a local minima. H at minus 5 comma 0 is
Minus 60.
0, 0, minus 6.
Local minimum.
Local maximum.
Maximum, right? Because the diagonal entry is negative. Determinant is positive and fx6 is
Minus
negative.
60 minus 60 is going to be positive. No?
Determinant is positive. After the determinant being positive, we should check for the diagonal entry. Since the diagonal entry is negative, it is a maxima. Here, since the diagonal entry is negative, it is a positive, it's a minima.
Okay.
Here. So after checking the determinant, we have to check for the sign of the second derivative. Okay, what is h of 3, 4? 36, 48,
36,
48, 36,
Minus 36.
36 into 1 minus
minus
2
36.
minus 36. So the determinant is negative, right?
Yes.
This here it is minus and then we'll get another minus. So determinant is negative. So this is a saddle point. I think for the other one also we will get a similar thing. Minus 36, minus 48, minus 48. I think here we'll get 36. So here again we'll have a saddle point. Right?
So what is the significance of this Hessian matrix being negative? Means how can we see into this graph?
Which one? In this case, is it?
Yeah, means saddle point being
so if
negative.
the determinant, if the determinant is negative, then we are going to get a saddle point. And saddle point means that we have a saddle in the function, in the graph of the function. Can you tell me this? We will plot. That is equal to x cube minus 2x cube plus 6y squared. 2x cube plus 6y.
6xy square.
xy squared minus y cube
Plus
plus
150.
150x minus 3y cube.
3y cube only.
Minus 3y cube
Minus
minus
150x.
What did I do? Right. Okay. Why is the graph looking like this?
It's look like a plane.
Yeah, I've done something wrong, I guess, because there's a curve also. I think the curve is what it should be.
Required to refresh the page refresh.
Oh, it shouldn't look like a plane. Yeah, z is equal to 2x cube
Plus 6xy square.
xy squared minus 3y cube minus
150x.
Okay, why is it still looking like a plane?
Yeah.
But it should look like this. Like this makes sense, right? Because we have a cubic equation. So this curve line that is there makes sense.
Two saddle points.
Oh, okay, we are in 3D, right? Yeah. Then. Okay, I don't know what is going wrong, but yeah, this is not obviously the function.
Maybe we need to multiply by or divide by a factor to enlarge it. Is it so? Because in 2D,
No, but even then it's on the XY plane, which is not right. Or not XY plane. What plane is this? It is on the XY.
If we didn't put that z, then what will happen? Only the function alone.
And then it's showing the same. If I write it as f of x comma y, then that z is equal to, right? What is the point that we got?
Yeah, what I was asking is Hessian matrix negative means saddle point. So what significance it is of Hessian matrix determinant? Means in graph if you somehow forget means if I forget means Hessian matrix either positive or negative. Whatever clause you have shown in the rules you have shown in the chapter, if I forgot those things. So significance wise, how my mind can remember these things. So I want to relate it with just with the graph.
Actually, there is no direct means. There's nothing that we can tell so that you can remember it that way. You have to remember the rules. Actually, the matrix, you want the matrix to be positive definite and negative definite and all that for maxima and minima. But yeah, to know all that, you need to know eigenvalues. So it's just, so all these conditions put together reduces to just one condition. A is positive definite. Then it is a maxima, I think, or minima, I don't remember. Positive definite means all will be positive, so it's minima. If it's negative definite, it will be a local maxima. If it is neither, then it will be a saddle point. So this is all that you have to remember. But since we don't know the eigenvalue concept, you have to remember it as separate conditions. So you have to remember the conditions. There's nothing else.
Okay, thank you.
Yeah. Okay, so let's do this problem. And we don't know what has gone wrong here, but something is wrong. Means I don't know if I'm doing something wrong.
Ma'am, it's 3y square, not 3y cube.
It is
3y square.
Oh. Something wrong with my laptop then? We did refresh, right?
Just refresh the GeoGebra because I have also faced this issue a lot of time.
Okay. Okay, can you quickly tell me what it is?
2x
cube
plus 6xy minus 3y square.
Minus 3y square.
Minus 150x.
Okay, till this looking nice, but when I put 150x, it's still bad. Okay, at least we have a 3D figure. Minus 1. So maybe we'll try out after some time. Okay. So let A denote the shortest distance from the origin to the plane, the value of A squared. What should we do here? We have some plane and then a point. What is the shortest distance from the origin? Oh, okay, origin. So we have the origin and we have the plane. What is the shortest distance? How do we calculate it?
It's the straight line x square plus y square plus z square.
Okay, the distance between any 2 points from the distance between the origin and any point on the plane is this. Right? This is the distance given that the point xyz lies on the plane. Right?
Yes.
Subject to the condition that z is equal to x plus y plus 3y. So the shortest distance that I have to calculate is this. Means I want to calculate the minimum of this. Right?
Yes.
Yeah. So minimum of this, calculating the minimum of this is equivalent to calculating the minimum of the square of this function, right? I can ignore the square root, right?
Yes.
Because when I take the partial derivative and all that, I'm just going to get 1 by 2 and some crazy powers. Instead, I can do this. Minimizing the square of this is same as minimizing this. So now I can take f of x comma y as x squared plus y squared plus x plus y plus 3 whole square. And I know how to find the minimum of this, right?
Take the derivative.
Fx and fy should be 0.
Fx, fy 0, Hessian, all that we'll do. Okay, so let's do that. X squared plus x squared 2x squared plus 2y squared plus 2xy plus 6x plus 6y plus 9. What is fx?
4x.
4x plus 2y plus 6. I want this to be equal to 0. Fy is 4y plus 2x plus 6. Okay, so we have two lines. They will intersect at one point, at most one point. So what is it? 2x plus y is equal to minus 3. X plus 2y is equal to minus 2. So 2, 4, minus 6, subtract. Minus 3y is equal to 3. Y is minus 1. And so x is minus 1, this side has plus 1, minus 2, minus 1. Right?
Yes.
Okay. So what is the Hessian matrix here? Fxx 4, Fxy 2, Fyy 4. Determinant is positive. Determinant is positive. Fxx is positive. So the only critical point has to be a point of right. So this is the point of minimum. But we are interested to find the point on the plane. So what is the point on the plane? X is equal to minus 1, y is equal to minus 1 and
0.
Minus 1, minus 1 plus 3.
1.
2,
1,
no? 1, no?
1.
because z is equal to x plus y plus 3.
Yes.
This is the point of minimum. And what is the minimum distance? This one, right?
Square root of 3 1 square minus
You want to find this is the point where the distance is minimum, and the distance from the origin is square root of 1 squared plus 1 squared plus 1 squared. 3. Okay, this should be minus 1 squared plus 1 squared. So this is my A. What is asked is A squared. Yeah. A is the shortest distance from the origin to the plane. So that's what we found out as root 3. We wanted A squared, so that's 3. So is it clear what we did?
Yes, ma'am.
Okay. Okay, I guess this will be the last problem for this. Yeah. So now what is happening? What is happening in this question?
Just a clarification on the above sum. So what we did is we found the minimum point and then we substituted that point in the function and then to obtain the shortest distance, and then we found the shortest distance. Is that a correct understanding?
Yeah. So we converted this into a function of two variables by substituting this first.
Okay.
So we will get a critical point with two components, x and y.
Okay.
But we are looking for a point in the plane, which means that there should be a third component, right?
Yeah.
That we will get by putting that condition. Z has to be x plus y plus 3. And then we found the distance from the origin. Means we know that this is the point where the distance is minimum. So we found that distance and whatever is asked.
Thank you.
In 2D we have learnt point to line distance. That same concept can be applied here. I think it will also work.
That works for any n tuple. Means x minus x1 whole square plus x
Y minus y1.
Y minus y1 whole square plus z minus z1 whole square. In fact, how many ever components it has, the same formula works. Here we are getting
this ax1 plus ay1 upon under root a square plus b square formula.
Where? Here?
The equation of line is given, and from line to point distance. So that formula is also there, no? Ax1 plus by1 plus c.
Yeah, but here we are not doing that. We have a point and we have another point 0, 0, 0. We are finding the distance between these 2 points here.
Yeah.
Here we are just given a plane, right?
Yeah, but this problem also can be solved by that thing also. It will be solved in one step. If this point is not asked in the question, then we can do it by point to a plane distance. There's direct formula, na? Ax1.
Yeah. Fine. Yes.
Perpendicular distance.
Geometrically, yes.
Yeah,
this is using the concept of the thing, maxima minima. Okay. So yeah, in this problem, f of x comma y is this. Be defined on a box. Okay. So in one variable case, when we are given an interval, a function is defined on an interval, we can talk about absolute maxima and absolute minima, right? The global maxima, global minima. How do we do that in one variable case? We find local maxima, local minima and all that. And then we evaluate at the end points also, right? You remember?
Yes.
Out of all these, whichever is the smallest will be the global minima, and whichever is the biggest will be the global maxima. So here we had the concept of end points. But when we are talking about in 2D, say we are in a rectangle, So what are end points here?
Four points are.
No, the entire thing is end, no? Means it's the boundary basically, right? Because when we calculate maxima, minima, we'll be dealing with the inside portion. So whatever is the boundary, that will be thing. It will be like end points. In fact, in boundary also, you have to split. So you have a box. You find out, you want to check what happens along this line. And then you check what happens along this line and this line and this line. But when you're talking about this line, again, you will be applying the thing like in one variable calculus, right? Because on this line, it will be a function of x alone, right?
Yes, ma'am.
So again at the end points, so the end points will be these 2 points. And here the end points will be these 2 points and all that. So you have to check on the boundary of the box and again on the 4 corners of the box as well. Okay, we'll do this, then maybe things will be clear. First, let's expand this function. 9x squared plus 36x squared y minus 1 minus 4y. Okay, and the box is minus 2 to 3, minus 2 to 3, minus 1 to 4. This is the region where we have to calculate the local maxima and minima. Okay, absolute maxima also we want. So absolute maxima, absolute minima. Okay, what is fx?
18x.
18x plus 72xy.
Right. So 18x into 1 plus 3 or 4.
4y.
4y equal to 0. So x is equal to 0 or y is equal to minus 1 by 4. What is fy? 36x squared
Minus 4.
Minus 4.
So x is equal to plus or minus 1 by 4, right? Oh, not 1 by 4. 1 by 9, 3, right?
Yes.
Yes.
So this is not possible. This has to be the only case. So the 2 points are 1 by 3 minus 1 by 4, minus 1 by 3, minus 1 by 4. Okay. What is the Hessian matrix? fxx, fxy is 72x, 72x, and then fyy is 0.
The
What
first
happened?
entry is wrong, I think.
Huh?
The first entry is wrong. It's 18 plus 72y.
Oh, okay, fine. Plus 72. Fine. So what is h of 1 by 3 comma minus 1 by 4? (18 minus 18, 0, right? Okay, 72x. 24, 24, 0. Determinant is negative, so this is a saddle point, right?
Ma'am, that 72x will remain 72 or it will be 72x minus 4?
72 by 4, 72x.
The upper
With respect to
the upper equation I installed. 9x square plus
f.
50.
This is fxy. Fx with respect to y.
Okay.
Or fy with respect to x. So 72x, no? 4 is a constant, it will go off and while differentiating.
Yes.
What about the other point? Minus, I think it will also be a saddle point. 0. Yeah, minus 24, minus 24, 0. This is also a saddle point, right?
Yes.
Yeah. So now inside of the box is done. Since we are looking for the outer part, means we are looking for a maximum on this, we need to consider the boundary as well. So what is this line?
3. Ma'am, how do we know we have done inside the box? Because of the points.
So when we are doing this concept of whatever we have studied, we are actually doing it in open ball. We are doing things in open ball. So when you do absolute maxima minima, what you're actually doing in the procedure is in the open ball, in the open interval. That is why you have to evaluate separately at the end points for absolute maxima and minima. So now whatever procedure we have done is done for this portion. We needn't consider any other points within the portion separately. Since we are given a box, we need to check at the end points also, means on the box also.
I think this procedure we have done is for plus infinity to minus infinity. It is in the space, whole space. Wherever this maximum minimum exists, by this procedure we will get. Yeah. Now we are defining.
Since we are restricted, now we will look at what happens on the box. Because it is on the box, first of all, this is a continuous function, right?
Yes.
So if we are talking about maxima, minima in a box, definitely maxima and minima will be attained, right?
Yeah, at the end point somewhere.
Somewhere definitely maxima, minima will be attained because it's a continuous function. So if it has to go outside the box, it's going to go continuously through the boundary of the box, and definitely there will be one point where there will be a maximum and one point where there is a minimum. Okay, so now what is this line?
3 equals to 3. Yes, x equals to 3.
X is equal to 3, right? And this line is
y equals to 4.
This is
X minus 1.
X is equal to minus 2, and this is y is equal to minus 1. Okay. So now along each of the lines, we have to calculate separately. Along y is equal to minus 1. Let's do that first. What happens to the function on that line?
So we put the value of in fx, right?
Fx comma minus 1. Because along this line, the value of the function will be with the points y is equal to minus 1. So I'll have 9x squared minus 36x squared minus 1 plus
36x.
No, y is minus 1, no?
Oh, sorry.
So this is minus 27x squared plus 3. Now it's a function of one variable, right?
Yes.
So I will find out the derivative. One variable procedure. Minus 54x is equal to 0. So x is equal to 0. F double dash is minus 54. So it is a point of maxima. What is a point of maxima?
X is equal to 0, y is equal to minus
1. This is a point of maxima. Okay. So since it's contributing, let's calculate what is the value of the function also. So here we can substitute. Simplest is to substitute here. put x is equal to 0 here. Okay. So this is the value it has contributed. Let's keep it aside. Next is x is equal to 3. Along x is equal to 3. F of 3 comma y. 9 into 9 plus 36 into 9 into y minus 1 minus 4. So 81, 9 6s are 54, 9 3s are 27, plus 5 is 32. Y minus
-1. Hello. Hello. Ma'am.
Hello.
I'm not audible. Blocking road.
So will it possible to continue this session or?
I think this was the last question.
This is the last question, but the question not completed.
Hello.
Yeah, hello all. So the meeting is over. So we will continue it on Friday. Okay.